Hello APC Mechanics students in Unit 1 Kinematics, Class 4, Free Fall Motion, Part 1. Section 1, Free Fall without initial velocity. An object said to be in free fall if the only force acting on the object is the force of gravity, a resistance must be negligible. Near the surface of a planet, the acceleration of a free fall is equal to the gravitational field strength of the planet. On Earth, the value of this acceleration is 9.8 meter per second square or 10 meter per second square. Remember that each planet is characterized by something called the gravitational field strength G, and near the surface of a planet G is constant. If you consider Earth, that would be 10 meter per second square or 9.8 meter per second square. So let me repeat and say again, an object is said to be in free fall if it's left to fall freely near the surface of a planet, and in this case a resistance must be negligible. Then the type of motion of this object is uniform varied motion, and its acceleration is equal to g, which is 10 meter per second square. Now in the coming sections we are only interested in the motion of a free fall without initial velocity, because you know that initial velocity is an important parameter or a variable that appears in the equations of motion. There is always a term related to the initial velocity. Here we're assuming that there is no initial velocity, so here an object is dropped with no initial velocity. This initial position coincides with the origin, and we choose the positive y direction to be downward along the direction of motion and acceleration. Acceleration is down at the rate of 10 meter per second square, and this position coincides with the initial instant given by t is equal to 0. Here we study the case of a free fall with no initial velocity I've mentioned. Starting from 0, the speed increases at the rate of 10 meter per second each second. Now, as we said that the acceleration is 10 meter per second square, and it can be written as 10 meters per second, which means that each second the speed is increasing at the rate of by a value of 10, which means 10 meter per second square. The acceleration, by that we say that the acceleration is generating the velocity downward. In the first second, the speed is 10. At t is 2 seconds, the speed is given by 20, then 30, 40, and 50. Now the covered distance increases quadratically each second. We know that in uniform varied motion, constant acceleration position is proportional or is expressed as quadratic in time, so the variation is gonna be quadratic. In the first second, the covered distance would be 5, then 15, 25, 35, 45. Here we're not measuring the position with respect to the origin. However, the covered distance for each time interval, and the time interval is given by 1 second. And it's important to remember the numbers given by 5, 15, 25, 35, 45. Let me repeat and say this is not the position measured with respect to the origin. However, the distance between two slices separated by a second. Okay? Now section 2, time lapse of a free fall without initial velocity. In this section we are interested in calculating the time required for an object released from rest to cover a distance h, which is the distance until it reaches the ground, for example. How we're gonna do that? First, we need to specify the type of motion. A free falling object is submitted to constant acceleration, and if we have the distance, so we have the position, say for example, and we are interested in calculating the time, given that the acceleration is g, then we are interested in the position time equation governed by uniform varied motion. We're gonna swap x by y because we have chosen the motion to be along the y direction. If the initial position coincides with the origin and the initial speed is 0, then that would give us the following. And we know that the final position is given by h and the acceleration is given by plus g, because downward is the positive direction of motion. In this case, we're gonna have that h is half gt square, or in other sense, if we isolate t would be given by 2h divided by g, and that would be t is given by radical 2h over g, then what does this represent? T represents the time taken for the object to cover a height h under the influence of gravity. So dw stands for the downward motion, is the time lapse for a free fall with no initial velocity to reach the ground. H is the falling height. G is the gravitational field strength near the surface of a planet. So whenever we have an object released from rest and it's gonna cover a distance h, the time required for this object to cover this distance is given by radical to h over g. But the thing is that we cannot ever use this formula unless the object is released from rest. So example 1, an object is dropped from the tip of Burj Khalifa. How much time required for this object to reach the ground? Now if we refer to the figure, or we know that the distance from the ground to the tip of Burj Khalifa is given by 830 meters, and here we suppose that the object is in free fall, no air resistance, and by dropped it means from rest. Then by that we can use the previous formula to calculate the time lapse. The time lapse is given by the square root to h over g. H is 830 and g is 9.81, and the total time would be 13 seconds, which is a remarkable value. Similarly, in the same manner, we can calculate the impact speed, because we know that as the object is falling under a free fall, its speed is increasing due to the generation of because acceleration is generating the velocity or the speed. So we can calculate the speed just before impact, before it hits the ground. Initially the position coincides with the origin. This is taken as the time equals to 0. Initial speed is 0. Now the type of motion, as we know, constant acceleration. Then here we need to calculate the final velocity given the initial velocity, given the height and the acceleration. Then we are interested in this equation. We swap x by y. The initial velocity is 0 and the initial position is 0, and we know that ay is g and y is h, and by that vy square is 2gh, so the final speed would be radical to gh. Now, so let me recap. Any object released from rest, the speed will increase under the influence of gravity or generated by the gravity. Before it hits the ground, its speed is given by radical to gh, but remember that we cannot ever use this formula if the object is released with initial velocity. We can only use it if the object is released without initial velocity. Vy would represent the velocity before impact, h is the falling height, and g is the value of the gravitational field strength near the surface of a planet. Now, if we refer to the previous example, we can calculate the speed of the object before it hits the ground. And in this case, v is given by radical to gh. Here we follow the same assumptions. No initial velocity and no air resistance. Then that would be 127.6 meter per second. How can we evaluate whether the speed is large or no? So let's convert it, for example, to kilometers per hour. And this is done by multiplying by 3.6, and the value of the speed is given by 459. And knowing that this speed is close to the greatest top speed achieved by supercars, like for example, which is Bugatti Chiron, and it has, so the greatest top speed is achieved by Bugatti Chiron, which is given by 490 kilometers per hour. Then this free fall for 13 seconds is enough to generate speed for the object given by that much. Now here let me introduce some nice application on what we have done. Motion on an inclined plane. An object is left freely at the top of a frictionless ramp with no initial velocity. Here we have a ramp inclined by theta. The elevation from the initial position of the object to the ground is given by h. H is the vertical distance. D would represent the distance that the object is gonna cover along the ramp. We have no friction and the object is released from rest. The results of the kinematics that we have done previously can be generalized and applied here. Then the velocity at the end of the ramp is given by v is radical to gh. Because the object is covering a vertical distance of h under the influence of gravity, Then the velocity at the end of the frictionless ramp v is given by radical 2gh, which is in analogy for the free fall motion. Also, the final velocity can be expressed as, now if you work out the trigonometry, sine of theta would be the opposite, which is h, over the hypotenuse with g. This is 90 degrees. Then h can be expressed as d sine theta. Then we can express the final velocity of the object in terms of d sine theta, where d represents the distance covered by the object along the ramp. Here we follow the same assumption. So suppose we have an object released from this point. It's gonna go over this curve, reach this point on the table, then it drops down to the ground. Now here the object will gain a speed v1, and here the object will gain another speed v2. During the downward motion, if we assume no friction and air resistance, under the influence of gravity, we expect that v1 is greater than v0 and v2 is greater than v1 as well. So v1 at this horizontal slice is given by radical 2gd. Why? Because it covered downward a distance d under the influence of gravity. Similarly here, v2 would be given by radical 2g d plus h, because h plus d would represent the vertical distance covered by the object from the initial position. Frictional forces are neglected and no initial velocity. The final velocity only depends on the vertical height descended by the object. Alright. And for the following set of exercises, I suggest that you pause the video, try to understand the question, and give it an attempt. Then let's start exercise 1. In the absence of air friction, an object dropped near the surface of the earth experiences a constant acceleration of about 9.8 meters per second squared. This means that, so if you check all the options, you're gonna see that this means that the speed of the object increases 9.8 meters per second each second, and the correct answer in this case would be A. Which of the following statements must be true for a falling object that has been dropped from rest near the surface of Earth? Here similarly, if you check the choices, the speed of the object increases by 9.8 meters per second during each second. Now exercise 3, an object is dropped from rest from the top of a 400 meter cliff on Earth. If air resistance is negligible, what is the distance the object travels during the first 6 seconds of its fall? Then we have a free fall because air resistance is negligible and it's released from rest. We're talking about distance and time, so we can directly use this relation, which is h is half at square. And we need to calculate the distance, not the time. So that would be half 9.81 multiplied by the time, which is 6 to the power of 2. And in this case, the correct answer would be given by 180 meters. If air resistance is negligible, the speed of a 2 kg sphere that falls from rest through a vertical displacement of 0.2 meters. So we know that this is air resistance is negligible and falls from rest, then we can directly use the impact speed. Then that would be radical to 9.81 multiplied by 0.2. And the impact speed would be given by almost 1.98 meters per second. And the closest to that would be B. Now exercise 5. Astronauts travel to another planet and wish to determine an accurate value for the acceleration due to gravity. They drop an object from the edge of a very tall cliff, and with a motion sensor collect the data shown. If air resistance is negligible, the magnitude of the acceleration of the projectile is most nearly. Air resistance is negligible, then it's a free fall. And let me see. Okay, they drop an object from the edge of a cliff. So here we assume from rest. Then we have time and we have distance. We're gonna use the equation given by h is half at square. And we need to calculate the magnitude of the acceleration. So a would be given by the double of h divided by t square. So let's use the first row. H represents the distance, which is 0.26 divided by t to the power of 2, then 0.1 to the power of 2. And plugging that on the calculator, the value is going to be closest to E, which is 52.8. In an experiment, an object is released from rest from the top of a building. Its speed v is measured as it reaches a point that is a distance d from the point of release. If the distance was doubled, we're gonna use the factor of change. Here we assume that air resistance is negligible, so we're the case in a free fall. Released from rest, so we can use directly v is radical 2gh, and now we can apply the factor of change. The distance is doubled, so that would be radical 2 didn't change, this is 1, and that would be 1, and h is 2, so it would be a factor of 2, radical 2, and the correct answer would be B. An object falls freely from rest under the influence of gravity. It's a free fall because air resistance is negligible. The ratio of the distances traveled during each 1 second time interval by the object during the first second and third seconds of its fall is. So remember that I told you to remember the distances given by the slices. So let me say it was given by 5 meters, 15 meters, 25 meters. This is 0 seconds, 1 second, 2 seconds, and that would be 3 seconds. So in the first and the 1 second time interval, that is given by 5, and in the second one is given by 15, and in the third one is given by 25. And now we can divide by 5 and by 5, that would be 1 over 3 over 5, which is expressed as 135, and the correct answer would be D. Okay, exercise A. The acceleration due to gravity on the moon is gm. Suppose an astronaut on the moon drops an object from a height h. The time would take the object to reach the moon's surface would be tm. The same object is dropped from the same height on Earth, so we have the same height. On moon, it's given by gm for a time tm. This is on moon. And on Earth, it's the same height, capital H, and this is g on Earth and t on Earth. The same object is dropped from the same height on Earth, where the acceleration due to gravity is ge. The time it takes the object to reach Earth's surface is te. Which of the following is the correct mathematical relationship for the two times? We need to find the relation between te and tm. So remember that, okay, here they didn't mention that air resistance is negligible, but we're gonna assume it, and it's released from rest. Then the time is given by radical 2h over g, and the best way to determine a relation between two variables is to calculate the ratio. So since we are interested in expressing te in terms of tm, so we'll say te divided by tm. That would be radical 2h over ge over radical 2h over gm. So here h is the same, so this cancel, and we're left with 1 over radical ge over 1 over radical gm, and this can be written as radical gm over ge. So te would be expressed as, let me say, radical gm over ge multiplied by tm, and in this case the correct answer would be B. Now two objects are dropped from rest from the same height. Object A falls through a distance ta during a time t. So let me say this is the object A. Okay, they are dropped from rest. Now, alright, so it's dA and t, and for object B it's given by dB and the double of t, A resistance is negligible. We're in the case of a free fall with no initial velocity. What's the relationship between dA and dB? The best way to do it is to calculate the ratio dA over dB. Why dA is in the numerator? Because we want to express dA in terms of dB. Now, the distance, as we know, is given by half AT square and half AT square. Let's put now the labels. Now here, since the two objects are dropped from rest from the same height, we assume that the acceleration is the same under the influence of gravity. This is TA and this is TB. That would be TA square over TB square. We know that the time of A is given by simply T, and the time of B is given by the double of B. That would be 1 over 4. So dA over dB is equal to 1 over 4. That means dA is 1 over 4 dB, and the correct answer is A. Finally, an airplane travels horizontally at a constant velocity v. An object is dropped from the plane. 1 second later, another object is dropped from the plane. If air resistance is negligible, what happens to the vertical distance between the two objects while they are both falling? Okay, dropped. Let's assume with no initial velocity. Let's assume with no vertical velocity. Now, because the plane is traveling horizontally, this will be discussed later during the projectile motion. However, now let's consider the slices of time. 0 second, 1 second, 2, 3. Since they are dropped after each other by a second, then they are separated by slices of time given by a second. This is 5, this is 15 meters, 25 meters, 35 meters. They're gonna fall, and each time they fall, they will occupy a slice of time. And we know that these slices of time, the distance between them is increasing. So 5, 15, 25, 35. For this reason, we will say, what happens to the vertical distance between the two objects while they are both falling? It increases. Then that's it for me in this video, guys. See you soon in a new one.